Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to welcome Bobby Kleinberg. So Bobby is one of the Microsoft new faculty fellow, and he's done great work on design and analysis of algorithms and applications to e-commerce, networking, and many other things. And he's going to tell us about network formation.
Okay. Well, thanks, Nikhil, for inviting me to come give this talk. This presentation will have sort of a Colts to Newcastle character to it, in that it's some work applying random graph theory and edge percolation to analyze network formation in the presence of contagious risk. And much of the technical content of what I'm going to present, while non-trivial for us, might be sort of an exercise for some of the people in this room. And so I encourage you to think of this talk as an introduction to a provocative branch of applied math about which very little is known, and which there's perhaps no more distinguished group of people all in one place to study these sorts of questions than I have right here in this room. Okay, so as I was thinking about the types of questions I'm going to get during this talk, that's not one that occurred to me.
That's what I will say.
So a lot of us are fascinated by the subject of complex networks, and when researchers have looked at why complex networks look the way they do, people take very different approaches toward answering that question depending whether they come from mathematics/physics or from social sciences. So those who like to address complex networks from a probabilistic perspective will come up with models of network formation that say something like links form according to the following simple rule. Nodes show up one at a time and link to other nodes with probability proportional to their degrees, or with some probability depending on your distance from other nodes in some host metric that's independent of the network topology. On the other hand, in the social sciences, you see models that don't have any explicit probability built into them at all. So nodes form a network based on an endogenous optimization process in which each of them constructs links strategically so as to optimize some payoff that depends on the global structure of the network that they form. An example of such a model, just to introduce you to the aspect of the theory that may be less familiar, is this one from Jackson and Walensky. So in this model, there are two parameters that define people's utilities for the network that gets formed. There's an alpha, which is the cost of forming a link, and a delta, which is some decay parameter that specifies how much of a preference you have for being close to nodes as opposed to far away from them. And then your payoff is linear in the number of links you form. So you experience a negative payoff, a cost of alpha, every time you form a link. And then for every other node in the network, you have positive payoff, which diminishes geometrically with your distance from that node. So for example, in a network where B and C are already linked together, and A is strategically deciding which subset of two possible links to form to them, it could either do the empty set with a payoff of 0, one link with this payoff, or two links with that payoff. And for different choices of delta and alpha, you can get each of these three behaviors to be utility optimizing for node A. so that you can sort of draw a phase space, in the two-dimensional space of alpha delta settings and plot the graphs that arise as optimal graphs at each point of the phase space. There's an interesting issue involved in defining what it means for a graph to be an equilibrium of this game. I trust that you're all familiar with Nash equilibrium, but generally Nash is not the right equilibrium concept for looking at network formation games, because Nash considers what happens when individuals make unilateral deviations, but the process of forming a link between two individuals should really be thought of as a bilateral process where both of them must willingly opt into forming the link. And accordingly, game theorists analyze these games using stability conditions that seem similar to Nash, but are not exactly Nash. The stability condition that will be relevant to this talk is the following one. We'll assume that any node can unilaterally secede from the entire network. It can delete all of its links. And that any two nodes can jointly decide to create a link between them if it benefits both of them and benefits at least one strictly. So a network is stable if neither of those two moves, if it's a local optimum under those two types of moves. So there's no individual that can strictly improve its payoff by seceding from the network, and there's no pair that can each weakly improve their payoff, and at least one strictly by forming a link between them.
So you're not allowing individuals to just cut off some of them?
We're not allowing individuals to cut off a subset of their nodes. And good. So any network which is stable under that stronger definition is stable under our definition. And so when we prove impossibility results for stable networks under our definition, they automatically carry over to impossibilities for stable ones under the other definition. But an existence theorem for stable networks under ours doesn't imply existence for the other. And so that's just something to bear in mind. Actually, I claim that the more interesting result about stability in this talk will be the impossibility one, which does carry over. But that's obviously a self-serving claim, so you're free to form your own opinion about which of the two is the more interesting.
But the reason for doing it that way is sort of because of what you can prove, or because that's an interesting, I guess that's also a matter of...
The reason, well, okay. Speaking as a participant in the research process, the reason we did this, we knew that a question of primary interest to us was going to be a price of anarchy type question that was comparing the social optimum against the set of all Nash equilibria. And so if we adopted the most permissive definition of stability and still got a strong price of anarchy separation, that would imply the same for a less permissive definition of stability. And so given that in any such talk, when I got to this slide, there was going to be controversy over what stability means, we wanted to make an initial choice of stability definition that would resolve that controversy in a way that's most favorable to saying the price of anarchy result is a strong one. That's what we did. All right. So good. Moving on. The Jackson-Walensky style payoff function that I just described is there are many other papers in the literature that propose different payoff functions, but nearly all of them have this mindset that there's a cost to link formation, and the benefit that you get indirectly from forming those costly links is that you make this connected world, and then we all benefit from being connected together in this network. But there is a different type of network formation process that occurs quite often in reality, where links are beneficial and we pay a cost for all being connected together. That will be the subject of this talk. So we originally got interested in this subject in 2009 because of financial contagion, where these are banks making loans to each other. And at least in the popular consciousness about what happened in the fall of 2008, there's this sense that a tidal wave of failure propagated through the network, and the economy paid a large cost for being too densely connected in the presence of this possibility of risk. So that, although each individual business arrangement was beneficial to the two parties involved, the overall outcome of constructing a densely interconnected web got us trapped in this risky situation. Okay, so here I have a picture of the loan network of the US federal banking structure. This is taken from Bech and Atelier. The models that I'm going to be talking about in this paper are undirected graphs, whereas this one is a directed graph whose edges represent A makes a loan to B. At some level, the reason that failure propagates through this network is because of something called counterparty risk. So these banks make overnight loans to each other. It's literally, at the end of one day, a bank that doesn't have enough cash on hand to fulfill its minimum reporting requirement mandated by the Fed will ask to borrow a small amount from another bank, so that in the morning, when the Fed has the right to inspect them and see if they have enough cash on hand, they will pass that inspection. And then they'll immediately give it back to the bank that loaned it to them. Unless they default, which, because these are giant banks, there's almost no chance that'll happen. But there's a small amount of risk anytime money is given from one party to another that it won't be given back. And so these risks of defaults were each individually viewed correctly as being extraordinarily unlikely events. It's just that there were so many of them that when a lot of them started happening at once, unexpected results came out of that. Now that I've told you about the general scheme of links benefit people, but being overly connected can be to the detriment of the individuals, it's possible to find examples of that cropping up all over the place. For example, sexual contacts are usually treated by the participating parties as being beneficial. But an excessive amount of linking carries attendant risks. In some sense, this one actually hews more closely to the story of my talk because this is an undirected graph. So the probability of spread of failure is symmetric when a link is formed between two individuals. Another example would come from covert organizations, things like networks of terrorists. So the organization benefits from individuals being linked together because it allows them to coordinate plans requiring more than one actor to execute the plan. And the danger is that if one of these people is captured and coercively interrogated, they may divulge the identities of others. And so the organization is at risk if it engages in an excessive amount of linking, and then one of the individuals is compromised. Okay. There's another example that's not in these slides for some reason. So exchanging private data could be another example of this. When I share my cell phone number with somebody, that benefits me because that person, presumably it's someone I wanted to share my phone number with. And it benefits me that they now have my personal information and can call me easily. But if that person shares their address book with someone else, who shares their address book with someone else, and eventually one of the people in this web turns out to be a spammer, then it was not beneficial to me that we formed that highly interconnected network. Okay, so now I'm ready to present the basic framework that we use to qualitatively analyze all of these situations. Although in each case it would be quite easy to find at least one qualitative feature that differentiates this abstract model from the banking application or the STD transmission application, or whichever one you want to pick apart. So we have nodes that are forming a network of max degree capital delta among each other. It's an undirected graph. And there are two important parameters of the model. I think I should write them down on the whiteboard since they'll only be on this slide for a minute, but they'll be referenced throughout the talk. So Q is the probability that a node fails spontaneously. And spontaneous failures are independent events, each with probability Q. In addition, each edge makes an independent decision whether to be live or blocked. The live edges are capable of transmitting failure, and the blocked ones are not. And P is the probability of an edge being live. And so the way this determines a set of failed nodes in the network is that first of all, every node that fails spontaneously fails. And secondly, everybody that didn't fail spontaneously also fails if they belong to a connected component containing a failed node in the subgraph of live edges.
So is there a time dimension for this?
There's no time dimension. There's a notion that first the network is formed and then the failure is revealed. But those are the only two stages of the game. So yeah, if your application is STDs, then you would want to have a time dimension, which is that's in some sense the primary way that the STD application differs from the abstract model. But that just is what it is. Okay, so now throughout the talk, we'll think of both spontaneous failures and transmission along edges as being rare events. So Q and P are both positive, but they're less than 1, significantly less than 1. So if a node has degree d sub I and failure probability phi sub I, then its payoff is linear in the number of links it forms. So that's A di. Let me see if the formula is on my next. Good. So if you can see the slide, then you can see the payoff formula. And if you can see this panel of the board, then you'll see the payoff formula even when the slide is gone. You get a payoff of di for every link you form, but only if you don't fail. If you do fail, you get a negative payoff of b, regardless of how many links you formed.
So, just to make sure,
Yeah.
So the liveness or otherwise of an edge only influences the spread of failure.
That's right. Not the payoff. Yeah, that's right. So you get benefit. If you don't fail, regardless of whether your edges were live or blocked, you reap the benefits of it. OK. We're going to be comparing graphs now according to a parameter which is the minimum welfare of any node in the network. This is another one of those points in the talk where someone could interrupt me and say, well, why did you decide to evaluate? So actually, a philosophical discussion I'd love to have is why computer scientists are so bent on taking a graph or an algorithm, summarizing it in a single number, and then just saying mine is 100 times better than yours because on this one-dimensional continuum, mine came out 100 times higher than yours. But OK, it's a fact of CS research that people seem bent on picking a single number that measures optimality, and then ranking things according to that number. And we choose min welfare. Now, there are many other natural choices we could have made. Average welfare would be a very natural one. We chose min welfare because at one point in this talk, I will present an argument that only works using the min welfare and not the average welfare. And I think I'll remember to tell you when that happens. But
is the version of the welfare of the top 1%.
Yeah, that's right. That's right. So that, I think, would actually be a pretty uninteresting parameter for analyzing this model. OK. And as I hinted earlier, a motivating question, not the only question that we'll address, but a motivating question throughout the talk has to do with price of anarchy. That is, comparing this parameter in a socially optimal graph, a graph that maximizes the min welfare, versus the same parameter in a stable graph under the stability definition I showed you before. OK, so now it's useful to do some thought experiments to map out a region of parameter space in which the question is interesting and distinguish it from regions in which the question is completely uninteresting. If A is less than BQP, what it means is that for any node A, the risk of forming a link to B, which is, OK, if B fails with probability Q and transmits that failure with probability P. So anytime I form a link, I get a negative BQP payoff from having formed the link. If that is less than, if that's greater than the benefit of forming the link, then we'll just get a big independent set. And so A less than BQP is an uninteresting part of the parameter range. If there's someone who I know for sure is going to fail, and A is greater than BP, then I would link to them anyway, despite knowing for certain that they're going to fail. So that's an uninteresting part of the parameter range. Similarly, if there is an edge that I know for certain is going to transmit failure, and A were greater than BQ, then I would still choose to form this edge, despite the fact that it's guaranteed to transmit failure. So based on these thought experiments, we want to be focusing on a range of parameters where A lies between BQP and the min of BP and BQ. Yeah?
I'm not sure by even the first one yet, because the probabilities aren't just additive. So maybe I have some failure probability from my other neighbors, so the cost of joining to B isn't as much as BQP, because it doesn't increase the probability by that much.
Could disconnect from everybody.
Yes, I understand what you're saying.
It's something to do with this, you also disconnect when you fail.
You would like to, you would just isolate yourself completely from the network.
It's sort of, OK. So there's another, I forgot to write this down. Another aspect of the model that I told you about is that people form a maximum of capital delta links. And we think of capital delta as a constant that doesn't scale with the network size. So I'm going to get to your question, but let me first talk about the bounded max degree. If you have unlimited max degree, then when the number of individuals in the world becomes astronomically large, you get into ridiculous solutions where people are, that's not true. They lose their payoff if they fail. In an early version of the model, we didn't have you lose your payoff if you fail. Then you have the pathology that people form tons of links because they know they're almost guaranteed to fail, but they're still getting a payoff of A for every link they form. Yeah. I don't know how to answer your question. So definitely in a network of two nodes, if A were less than BQP, they wouldn't form the link. but you're making a valid point that the same argument does not.
But I mean, you've always got the option of disconnecting yourself totally. It seems like if A is less than BQP, that's one thing you would do. I mean, given that P and Q are very small, you might just...
Yeah, but it's still, if I have 100 links, then the first one increases my failure probability by BQP, but the second one by a little less than that. And so it's at least possible that for very large degrees,
But since you assume delta is bounded, the inequality will hold up to a constant.
Yes. Yeah, but the justification for delta bounded was also not completely airtight. Okay, so the paper makes a lot of assumptions to get into an interesting range of parameters where I think an interesting phenomenon is observed. And I have argued too forcefully and thereby gotten into a bit of trouble claiming that every other part of the parameter space is uninteresting. I haven't even gotten to this last line, which is an important one actually and is entirely unjustified. So rather than merely assuming A is between these trivial upper bounds and lower bounds, I'm going to assume that it has a lot of room on either side. So it differs from the min of BP and BQ by a factor delta, which is small, and exceeds the other one by delta inverse. So the important one here actually is the A less than delta min of BP and BQ. And it's important enough that I'm going to include it on my cheat sheet here. And I think the cheat sheet is now complete, which is good because I think if I wrote down here, nobody could actually see it. OK, so now it's possible for me to tell you about our main results. So it turns out that payoff A over P, which is the payoff that you would get from forming 1 over P links if you were guaranteed not to fail, is sort of it's a range in payoff space where a critical transition takes place. And we'll see that as delta tends to 0, the min welfare of a socially optimal graph is A over P times a constant which is strictly greater than 1 by an amount that's tending to 0 with delta. All of this suppresses the dependence on n, the network size, because it turns out that the limit of the optimal min welfare as n goes to infinity is a constant not depending on n. In qualitative terms, what this is saying is that socially optimal graphs actually push up to and slightly beyond a phase transition point in payoff space. And one thing that we'll see is that in order to get payoffs beyond this phase transition, you need to be able to know the identities of the people you're linking to. So in an anonymous model where each individual just chooses their degree and then a random graph with that degree sequence is generated, it's not possible for them to achieve payoffs exceeding A over P by any constant factor. We'll also see that in stable graphs, the largest min welfare achievable is little o of A over P as delta goes to 0. So it's bounded by G of delta times A over P, where G of delta tends to 0 with delta. And in qualitative terms, what's going on is compared to socially optimal graphs, stable graphs have a higher average degree, which exposes their nodes to a greater amount of risk, so much so that it wipes away all but a vanishingly small fraction of the benefit achieved by doing that linking. And this is a form of tragedy of the commons where because the individuals do not feel most of the negative impacts that they generate on others, they continue engaging in behaviors that are detrimental to society as a whole while making small increases in their own payoff until the general payoff shared by everybody is close to 0. OK, so I'd like to talk now about how some of these results are proved. So recall that we're forming a graph. Nodes spontaneously fail with probability Q, and edges are live with probability P. So this is edge percolation in a graph which is endogenous to the model. So in particular, when people happen to form a complete graph, then the live edge subgraph is a GNP. And as is well known, in GNP, where P is less than 1 over n by a constant factor, all of the components are small. So the probability of a component size exceeding S is exponentially small in S. And on the other hand, when P is 1 plus x over n, there's a giant component whose size is a constant fraction of n, the constant depending on this x in the numerator. And if you plot the dependence, it's 0 all the way up until the numerator is equal to 1. And then it immediately takes off with a positive derivative. There's a discontinuity in the derivative at 1. So that'll be important in the talk also. The derivative here is positive but not infinite. OK. So in analyzing the min welfare of arbitrary networks, we need to consider not just GNP, but edge percolation in general graphs of max degree capital delta. And I want to start out by showing you that the min welfare cannot exceed A over P by very much. So to do so, let me remind you of a little bit of the existence proof of the giant component. So if you just want to prove that there's a constant probability of forming a giant component in GNP when P is 1 plus x over n, you imagine performing breadth-first search starting from any root node. And in any step of this breadth-first search, you expose all of its adjacent edges. Some number of additional nodes are found and placed into the back of a queue. And so the expected change in the queue size is 1 plus x for the new nodes that show up, minus 1 for the node that was just inspected. So there's a positive drift in this random walk. And for our purposes, the only thing that is necessary for our analysis is that there is a constant probability that this random walk process continues beyond 1 over p steps. OK, so this is just a picture of the edge exposure process in the random walk. So then if we have a graph with minimum degree d, and we do edge percolation where the min expected degree of vertices is 1 plus x for some constant x greater than 0. What this argument establishes is that for any node I, there's a constant probability that its live edge component contains at least epsilon times d nodes. If you think about the consequence in terms of payoffs to nodes, that means that if you want everybody to get payoff 1 plus x times a over p, you need to have minimum degree at least 1 plus x over p. Is there a...
Don't you want p times d minus 1?
We're thinking of d...
You're taking off 1 and then adding d minus 1 others. So typically,
yeah, we're in the large D regime, so. But yeah. No, I should make a note for the next version of these slides. Yeah, because that's right. You only expose d minus 1. There's the edge you came in on that doesn't get re-exposed. Yeah. Will be fixed in the next version of these slides. If everybody's getting a payoff of 1 plus x times a over p, they get a payoff of A per link. So they must be forming 1 plus x over p links. So they're getting expected degree 1 plus x. So that means everybody has a constant probability of being in a live edge component with this many nodes. When that happens, their probability of failing is, let's see, I'm out of space to write on my cheat sheet. I can just do this in the air. Oh, there is, OK. Their probability of surviving is 1 minus q to the power epsilon d, right? And OK, we're taking d to be roughly a over p. And my a OK, d is roughly a over p, which is like delta b. So my I don't know how to do this in this amount of space. People have such a high failure probability that it washes away all of the benefit of linking and they get a negative payoff. They get a positive payoff of a over p if they survive. If they fail, they get a negative payoff of b, which is like a over delta p. So the only way this is beneficial for them is if their survival probability is like 1 minus delta. But it's much worse than that. OK, so that shows that if x is fixed, and I take delta p and q to be small enough with respect to that fixed x, then people cannot achieve a payoff of 1 plus x a over p. On the other hand, if we treat delta as fixed and we allow x to be sufficiently small, then I'll show you that you can get payoffs that are strictly greater than a over p. OK, so it's useful to think of two natural ways of achieving this. One is a bunch of disjoint clicks. And in that case, to get up to this level of payoff, we're going to need to have the degree be slightly more than 1 over p. So the click size has to be a little more than 1 over p. And then what's going to happen is we're going to form a bunch of disjoint GNPs for this value of n. And the other way would be to make a gigantic high growth graph, which basically looks like a deregular, locally looks like a deregular tree in the realm of a very slightly supercritical branching process. OK, so in the paper, we do general p and q sufficiently small. In this next set of slides, focus on the case p equals q. And let's think about which of these two types of networks is better. Good. So starting from degree 1 over p, should you increase your degree to 1 plus x over p for a very small x? If you do, you'll gain ax over p from forming those links. And you lose b times the increase in your failure probability. And we know that your failure probability depends, in the GNP case, on the giant component size, and in the branching process case, on the size of the component of the branching process containing the root. All right. OK, so here I've drawn the anonymous case. So that's a random deregular graph on n nodes. D is slightly more than a over p. So it has high girth and locally in a neighborhood of the root. the live edge subgraph is going to look like a supercritical branching process. So the size of the giant live edge component is going to be tau of x times n, where tau is another one of these functions that's 0 up until x hits 1, and then, sorry, the way I've parameterized it is 0 until x hits 0, and then it takes off with positive derivative. Right. So as you increase your degree from a over p to 1 plus x times a over p, what's happening is that your failure probability is increasing at a rate which is the derivative of tau at 0. So you're getting a benefit of ax over p from the links, and your failure probability is increasing by x tau prime of 0. So this benefits you if a over p is greater than b tau prime of 0. But I'm assuming that a over p is much less than b. A over p is less than delta b, and delta is a sufficiently small parameter. So in an anonymous market, it does not benefit you to increase your degree at all, but beyond the thresholds of forming of criticality. OK, that's what this hand-wavy argument was meant to convince you of. So now let's look at the opposite case where you're forming cliques, each of which is going to sample a live edge component, which is a GNP of expected degree slightly larger than 1. And let's do the same thought experiment. You start with clique size 1 over p, and you consider, is it beneficial to grow up to 1 plus x times p? So now what happens is the clique that node I belongs to is going to have a giant component of size theta of x times 1 over p. And in order for I to fail, the most likely cause of failure is that it belongs to the giant component and somebody in the giant component spontaneously fails. There are these other events that have truly tiny probability where I belongs to one of the other components and somebody else in that tiny component fails. These contribute negligibly. So, you know, of each of these three cases, I doesn't fail in this picture because it's in the giant component, but the only failures happen outside. I doesn't even belong to the giant component. The only case that's bad for I is that both it and the failed node. I'm making an assumption, by the way, that there's only one failed node here. It's a reasonable assumption because spontaneous failures happen with probability p. So the expected number of failures is 1 plus x. So the actual number of failures is Poisson with expectation nearly 1. So maybe there's not one, but a couple nodes that fail. But OK, so a constant number of nodes are failing. I is in trouble if it belongs to the giant component, and at least one of the failures is also in there. And so as you increase from 1 over p to 1 plus x over p, the benefit to I is, again, a gain in payoff of ax over p. And the detriment to I is negative b times the derivative of theta squared. So, OK, so once again, we're comparing ax over p versus 2bx theta of x theta prime of 0. And growing beyond the phase transition is beneficial if a over p is greater than 2b theta of x theta prime of 0. And what happens now, since we're thinking now of b, q, delta as being fixed, and x is allowed to be as small as we want, we can always set x small enough that a over p is greater than 2b theta of x theta prime of 0. And it means if we push past the phase transition by a sufficiently small amount, people's payoffs are still growing. So again, the qualitative reason for this is that in the branching process, if you're in a giant component, it's so large that you're virtually guaranteed to fail. And if you're in a bunch of small cliques, then you need two events to happen. you need to be in the giant component, and the failed guy needs to be in the giant component. And so it's really the difference between theta itself, which has positive derivative at 0, and theta squared, whose derivative is 0. That's what determines the qualitatively different behavior between growing clicks past the phase transition versus growing the degree of a branching process past the phase transition. OK. So this slide is just summarizing what I've talked about. So you can achieve supercritical payoffs by forming disjoint clicks. And if you're doing anonymous linking, that's impossible, because giant components in this case are much larger than giant components in this case. And so as soon as you get past the phase transition, the penalty of going beyond that transition is too steep. OK, so now for the final part of this talk, I'm going to talk a little about stable graphs. Remember, I advertised this price of anarchy result that says that there's a tragedy of commons where additional linking washes out almost all of the positive benefit that people get from forming these links. So in particular, we just saw that a union of cliques of size just barely beyond A over P gets a payoff which is actually reasonably high. So why is that graph not stable already in and of itself? I mean, after all, sorry, thanks. Not A over P. 1 plus X over P. Right. So these clicks are already getting pretty close to, they're past the phase transition. So if they grow a little more, the giant component is getting bigger reasonably fast. So you might think that this graph is already stable because there's not much room to grow the clicks. But if these two guys form a single link between them, then they get a benefit of A. The cost of forming that link is really just the probability that the node I linked to belonged to the giant component in its graph and someone in that giant component failed. OK. And that's small enough that if these are optimally sized cliques, these two nodes are going to benefit by forming that link. So what's going on here is forming that link doesn't expose INJ to very much failure. But because each of them is so highly connected to its own community, that probability of failure multiplies over everybody that's linked over I and J. So the total amount of negative utility that they create for the world by forming that link is much greater than the positive utility that they get. This is a form of the tragedy of the commons where OK, so the original tragedy of the commons story is there's a pasture. Everybody puts their cows out to graze on the pasture. And the farmers have an infinite supply of cows. And they're just going to keep putting cows on the pasture as long as the farmer gets additional benefit from that. And the model of the pasture is that it produces a net benefit, which is a function of the number of cows grazing it, a decreasing function of the number of cows grazing it, that eventually decreases to 0. And that net benefit is shared equally among the cows. Okay? So then from the standpoint of any individual farmer, if the benefit has not yet reached 0, they're going to put one additional cow on, because that cow will still get a positive benefit from grazing. And the farmer's total share of the benefit is going up because the farmer is increasing its number of cows. So you end up with this phenomenon that they keep populating the pasture until the total benefit to everybody is 0. The same thing is going to happen in our model. So people will just keep linking and linking until they've eaten up essentially all of the utility that they got from the linking. And that's the only time they stop. So how do you actually analyze it? Let's consider two nodes I and J in a graph where they have decided not to link to each other. If they decide not to link, that means that each of them, there are two reasons for them to decide not to link. One is that either I or J is already at its degree threshold, capital delta, and the rules of the game don't allow it to form another link. The other possibility is that one of them has a failure probability that's high enough that the link doesn't benefit the other party. Right? So the benefit to I, if it forms the link, is A, and the cost of forming the link is at most B times P times the failure probability of J. It might be strictly less than this, because maybe there's already another path from J to I in the graph, and so maybe I is already absorbing some fraction of the probability of J failing. But okay, all we're going to need is that the cost is less than or equal to BP phi J. So if I doesn't want to link, that must mean the benefit is less than or equal to the cost, and so the failure probability of J is already at least A over BP. So now let's think about three types of nodes. Those who are already at their max degree, and that's why they're not linking. Those who have failure probability greater than A over BP, and that's why nobody is linking to them anymore. And the third type of nodes have low degree and low risk. OK. So if we're in a stable graph, then every node must be one of these three types. And furthermore, the nodes of type 3 must form a clique. Because I've just argued that if I and J both have degree below capital delta, and they both have risk less than A over BP, then they're going to link to each other. OK, good. So the nodes of type 1 already have high degree. The nodes of type 2, yes?
Nodes of type 3 would form a clique if it weren't for delta. I mean, they try to form a clique and delta blocks them, no?
Nodes of type 3.
Yeah.
Because they're type 3, that means that they don't have type 1. So their degree is not capital delta.
There's many of them. They try to form a clique and they go above delta, right?
Then I wouldn't call them type 3. So consider a graph which is already stable. Its nodes have types 1, 2, and 3. The nodes of type 3, by definition, don't have degree delta. And by the argument on the preceding slide, they are already linked together in a clique. Because by our assumption that the graph is stable, there couldn't be any missing edges between them. That also means there are not very many of them. Because in a clique of max degree capital delta, you know that you have at most capital delta plus 1 nodes. OK, so suppose now, for contradiction, that everybody achieves a payoff greater than or equal to epsilon A over P. It means that the type 2 nodes have a payoff which is at least epsilon A over P. And on the other hand, type 2 means that your phi J is reasonably large, A over BP. So these nodes are getting a payoff of AdJ minus A over P, which is at least epsilon A over P. It implies that dj is greater than or equal to 1 plus epsilon over P. Good. So types 1 and 2 both have degree greater than or equal to 1 plus epsilon over P. I'm silently here making the assumption that capital delta is greater than 1 plus epsilon over P. But again, that's the interesting part of the parameter space, because we just saw the sort of optimal cliques have size 1 plus x over P. So if your max degree bound is significantly less than 1 over P, then the world is not even able to get up to the size of GNPs where giant components start to emerge. OK. So if there were no nodes of type 3, we would be in a graph of min degree 1 plus epsilon over P. We'd be doing edge percolation with probability P. And we already saw that that process produces for every node a constant probability of belonging to a component of size at least constant over P. And that eats up all of the positive benefit from linking and gives them a negative payoff. So if nodes of type 3 didn't exist, we would already be done at this point. We would have reached a contradiction because we assumed everybody's payoff is at least epsilon A over P and deduced that their payoffs were negative. Since we have the type 3 nodes, we have to do a little finesse to finish the argument. So assume now that the number of nodes in the world is very, very big. bigger than delta to the power delta. We have this clique of type 3 nodes, which, as I said, has at most delta plus 1 members in it. And that means within a hop distance of capital delta, you can only encounter about delta to the power delta nodes. If n is bigger than that, then there must be somebody who's far from this clique. And within delta hops of this node, you see nothing but high degree nodes. So now run the same breadth first search argument starting from this node. And you know that in the first delta steps of that breadth first search, you'll never expose one of these type 3 nodes, so it's as if they didn't exist. And the first capital delta steps are already enough to get the constant probability of being in a component of constant over p many nodes. So when n is that large, we take one of these far nodes and deduce that it has a negative payoff, contradicting our assumption that everybody's payoff is at least epsilon a over p. So that's the story of what happens in stable graphs. This proves that, in this parameter range that I delineated, people will do so much linking that they eat up almost all of the utility gain from forming links. So just a final slide of reflections and open questions before I end the talk. I guess the two main qualitative conclusions of this research were, first of all, when we first started thinking about this contagion model, a natural guess was that optimal graphs would consist of cliques that go right up to but not beyond the point where the giant component emerges. It's a natural guess because as soon as the giant component emerges, then there's a sharp transition in the behavior of failure propagation, and it's natural to think, well, that's eating up so much utility that you would push right up to the phase transition but not past it. We've seen that that's actually not true. You push past the phase transition by a small amount. You're able to get just barely supercritical payoffs, but not, but by a factor that tends to 0 with this delta parameter. And the other qualitative insight that we saw is that when you form Nash stable graphs as opposed to socially optimal ones, they are much less benefit for their nodes, as measured by this min welfare function. So one of the open questions we'd like to answer is it also the case that the average welfare in stable graphs is bad? And that translates pretty crisply into a question about the expected sum of squares of the sizes of percolation clusters in a graph of average degree 1 plus epsilon over p when you're doing edge percolation with probability p. And it's possible, actually, that the answer to this question is well known and we just don't know it.
The value is right at the critical point.
And this is known for irregular graphs and not just for regular graphs? So this is definitely in yes, for Erdos. Right. The question is, if I have a graph whose average degree is 1 plus epsilon over p, but it's not a deregular graph, it could have highly irregular degree distribution, is it still the case that the expected sum of percolation cluster sizes squared diverges the way it does for Erdos-Renyi?
No, but you're still, in all these cases, you're assuming some of the degree is high.
Yes. We're assuming the average degree is high, so we don't want to assume that the min degree is high.
Well, in some of your considerations, you assume the min degree little, which you call little d, which was so large.
So in some of our lemmas, we assume that the min degree is large. But then, when I had to analyze stable graphs, the way I honestly achieved that was I showed that stability implies that all the low degree nodes are in a clique over here, and then I went over here. So I had to work for that min degree. And the way I was able to obtain it was, so this is why we're stuck on min welfare instead of average welfare, right? the way I obtained this picture was by assuming that everybody's payoff is at least epsilon A over P. So now you see why this question about average welfare becomes a question about graphs of average degree D instead of min degree D. And it's possible that there's an easy answer to that question. We thought about it a bit and didn't see how to do it ourselves, but I'd love it if one of you would enlighten us. We also don't know what the structure of socially optimal graphs is. So I showed you that a union of clicks can get beyond A over P, and that nothing can get beyond A over P by a factor much bigger than 1. But we have no strong reason to believe that a union of clicks is literally the optimal graph, and it might be interesting to prove or disprove that conjecture. Similar structural question about stable graphs. So in our paper, we show that there exists a clique size such that a union of clicks of that size is stable. But there might be sort of many other stable graphs. And an interesting style of question is whether sort of all nearly optimal graphs or all stable graphs must look like a union of clicks with just a small number of edges added and deleted. Okay, and finally, for those in the room who are interested in modeling type questions as opposed to this is a math problem we couldn't solve that comes directly out of our paper. So then, can you extend the model to change the payoff structure of the game in some way that makes the users internalize the cost of linking so that the outcome of playing the game to a stable outcome looks more like the social optimum and less like these stable graphs where the tragedy of commons has set in and we've eaten up all the payoff. Okay, so thank you for your time, and I'm happy to stay and take questions.